Good evening. I'm Dr. Ofiare from the High Frequency Electronic Group at the University of Glasgow, presenting a paper on the investigation of plasma-induced edge damage and changes in GaN HEMTs for the INCAPE 2021 conference. GaN HEMTs have demonstrated the potential for meeting the requirements for high temperature and high power switching applications due to the high breakdown electric field, the thermal conductivity, and the wide band gap. GaN has a band gap of 3.4 electron volts and high breakdown electric field of 3.3 megavolt per centimeter, also with high electron saturation velocity and high density carriers, which have very high mobility due to the presence of a two-dimensional electron gas. This allows GaN to be used for both low voltage, medium voltage, and up to higher voltage applications. This desirable qualities of GaN also allows GaN to be used in high frequency applications such as the fabrication of microwave, millimeter wave, and RF amplifiers for space and radar electronics application, and also for power electronics applications such as switch mode power supply, DC converters, and electric vehicles. Depending on the voltage level, GaN can be used for both IT and consumer electronics for automotive applications and high voltage industry. To realize most of these applications of GaN, etching is sometimes required, where part of the epi layer or passivation is selectively removed to fully make the device. There are two main methods of etching. One is the wet etching and dry etching. For wet etching, which is usually done in a beaker with in a solution, the material is removed by chemical process. And for dry etching, this is done using plasma and gases, where the material is removed both by mixture of chemical and physical bombardment. An isotropic etch is usually desired over isotropic etch, where the etching is done in one direction compared to isotropic etch, where the etching is done in all directions, as shown in the image here. There are two main tools for plasma etching. One is the inductive coupled plasma tool, where the ICP power controls the ion density and the bias power controls the ion energy separately. Here, the substrate is not part of the plasma region, and this which leads to low ion bombardment on the substrate, leading to lower plasma damage. The second most used tool for plasma etching is the reactive ion etching tool. Here, only one power controls both the ion density and ion energy. And the substrate is part of the plasma generation region, and we have higher ion bombardment to the substrate, which leads to higher plasma damage. Here's an image of a ICP tool, which shows the ICP power to the coils and the bias power to the table. And the RIE tool, the only one power is on to the tool, which controls both the ion density and ion energy. Both images here are courtesy of Oxford Instruments. ICP generally provides better performance compared to RIE, but both can lead to damage on the device, which is caused by nitrogen vacancies and GaN band bending. To investigate this effect, 3 devices were fabricated. In device 1, shown here, the silicon dioxide passivation was etched and the gate was deposited using the same photolithography step. For device 2, which is similar to device 1, the silicon dioxide was etched and the gate metal was deposited. The difference between device 2 and device 1, 2 different photolithography steps were used, one to etch the silicon dioxide and the other for the gate metal deposition. This results in a area where the gate completely fills the etched area compared to device 1, where there are gaps left between the gates and the etched region. A third device called device number 3 was used as a control device which on device number 3, there's no plasma to the gate region, and the silicon dioxide passivation was employed after the gate metal deposition. All three devices are gate wraparound devices with ohmic metal stack of titanium, nickel, aluminum, gold, and 100 nanometers of silicon dioxide passivation. All the devices, the silicon dioxide was etched using the RIE tool with fluoroform gas, and the gate metal on all three devices are nickel and gold. The device dimensions are gate length, have a gate length of 4 micron, gate to source distance of 4 micron, gate to drain distance of 5 micron, and a gate width of 75 micron. For device number 1 and device number 2, measured characteristics after fabrication shows very low drain current in the microampere range compared to device number 3, which had no plasma on the gate region. And device number 3 has a drain current of 450 milliamperes per millimeter. This is a clear indication of the plasma damage on device number 1 and device number 2. To recover the plasma-induced damage on device number 1 and device number 2, two-step post-gate annealing process was performed using optimized condition. For the first post-gate annealing step, this was done at 400 degrees for 10 minutes in nitrogen. And as can be seen from this image here, the drain current increases to 850 milliamperes per millimeter after this first step. And this is increased further to 900 milliamperes per millimeter after the second anneal step, which was done at 500 degrees for 5 minutes in nitrogen. There's also better self-heating behavior after the second anneal step and stable transfer characteristics, as can be seen in the graph here. Device number 2 showed similar behavior to device number 1, where the drain current increases to 900 milliamperes per millimeter after the first anneal step, and this increases further to 1000 milliamperes per millimeter after the second anneal step with better self-heating behavior and stable transfer characteristics. Device number 3 also showed an increase in drain current after the first anneal step from 450 milliamperes per millimeter to 1100 milliamperes per millimeter after the first anneal step. This remained the same after the second anneal step, but with stable, better self-heating behavior and stable transfer characteristics. This table here shows the measured characteristics as fabricated and after the first and second anneal step. For all three devices, there's an increase in drain current after the first and second anneal step, but there's a reduction in the transconductance after the second anneal step, but they all show better, more stable transfer characteristics and self-heating behavior. The measured gate leakage current for devices number 1, 2, and 3 are shown in figures A, B, and C. For device 1, there's not much change after the first and second anneal step. For device number 2, the gate leakage is improved after the second anneal step, but for device number 3, the gate leakage gets slightly worse after the second anneal step. This has to be investigated further. In conclusion, we have shown that plasma damage can be observed on devices due to plasma etching, and this leads to very poor device characteristics. This plasma damage can also be recovered using post-gate annealing, and two-step post-gate annealing both improves the device characteristics with better self-heating behavior and more stable transfer characteristics. Also, in conclusion, we have seen that avoiding exposure of plasma to the device active region benefits the device performance. Thank you.